We'll start this afternoon session. We still only have 9 participants. Suppose they will start joining after their lunches or dinners. But anyway, we will start with Jorge Delgado now, and he will give a hands-on session, in particular about the numerical integration of partial differential equations.
Thank you, Antonio. So, hi, my name is Jorge Delgado, and as Antonio said, I'm here to give two hands-on lectures on numerical integrations of partial differential equations, also known as PDEs. And for that, I will give you a tutorial on this solver called FIDISOL or CADSOL. I will just call CADSOL just to be a bit more easier. So in this first lecture, I will try to explain a bit how CADSOL solver works, and we will also obtain a numerical Kerr solution. In the next lecture tomorrow, I'll give you a boson star, scalar boson star with rotation solution, and with that solution we'll use it to obtain physical quantities such as mass, angular momentum, and other quantities. So let's begin. So what is CADSOL? What is this solver? It's a professional package written in Fortran 19 that was developed by a team in Karlsruhe, if I'm not mistaken by the name, and can solve non-linear systems of partial differential equations. These differential equations can be 2- or 3-dimensional. They can be elliptic or parabolic, and they can be subjected to arbitrary boundary conditions on a rectangular domain. The solver uses a finite difference method, which is a Newton-Raphson method, and can use self-adapting grid and some arbitrary consistency order. The solver also provides, this is quite a feature of the solver, error estimations for the compute solution. So just to remind what is the Newton-Raphson method, for those who don't remember, it's a very simple method to find the roots of some function by using the derivative of that function. You can obtain the root by implementing this equation iteratively, as you can see by the animation. But this method also can find functions, and this is what FIDISOL or CADSOL does. So since it's a Newton-Raphson method, there are some aspects that are expected. The first one is that the system of PDEs must be written in this form, where all the equations in the system must be written. Basically, all the terms should be on the left side and should be equal to 0. So here, x and y are the coordinates, basically the independent variables. U is the set of functions that we want to compute, and ux and uy is the first derivative of those functions, and these 3 are the second derivatives. Then you also must provide the Jacobian for all the functions. So this can be easily computed by the derivative of p with respect to all the functions. And also a good initial guess must be provided. And finally, you can also provide, or you have to provide the boundary conditions in order to solve the PDE, and as well as a mesh for, in this case, for our case, a mesh for the independent variables with n x and n y points. So how does the solver really works? You start with an initial guess for u1 that does not solve the system of PDEs. Then you introduce an improved solution in such a way where we have the initial solution plus some difference. So here x is just a relaxing factor, which usually is equal to 1, and then we have some delta, which basically is just a difference from the initial solution. Then we also say or impose that this new solution solves the system of PDEs. Then you can expand this P of U2 in the small parameter delta U to first order and obtain this equation here. This equation, this we know because you know the initial guess, so you just have to compute the derivatives and you'll give an answer. This is the Jacobian that we must provide, so this also we also know. So we can compute this delta U. And this was what I just said. So you can use now equation 1, this equation, to obtain the second or the new improved solution. If you do this iteratively, this lasts 3 steps until we are lower than the prescribed tolerance, we should have a good answer for the system of PDEs. This model also came with some caveats. The first one is associated to the initial guess. So the initial guess must be close to the real solution, cannot be arbitrarily far away from that. So basically, this shouldn't be very, very far from 0. The second one is associated with this equation. Here it appears to be easy to solve this, but in fact what you have here is a vector. The Jacobians are matrices, and this also is a vector. So in order to find delta U, we need to do inverse matrices. We have to solve a linear system, and this is easier said than done. But this solver also provides several linear solvers. Then you just have the users just have to specify which of the linear solvers you want to use, and the CADSOL will do everything for you. So that's a little less of a problem. So about the error estimation, as I said, CADSOL can provide error estimates for the solution. And these errors are composed of the Newton residuals, so the P of U of n, the last step, and also the discrimination errors for the derivatives of the functions. Here, the solver uses a backwards finite difference method to do the discrimination. And obviously, when you do discrimination, that will always have some little error. Then, you can also do our own error estimations using, in this case, black hole physics results, such as the Smart law, the first law of thermodynamics. Now that I have explained a bit of the solver, you can now go and try to obtain a Kerr solution. So, as you know from earlier lectures, the Kerr solution is one of the most, if not the most, relevant solution in general relativity, and in Boyle linguist coordinates can be written in this way. But now you can imagine that what if Kerr never found that solution? What if there wasn't some mathematician guy that could not find this solution? What I have to do? You can use a numerical approach, and for that we use obviously the Kerr solver, the CADSOL. So in order to do this, we first have to impose or have to introduce an ansatz matrix. So here we use this type of ansatz. So here I have some colors just to try to remember which is which. So in red we have the ansatz functions. So F0, F1, F2, and W. In blue we have some function that we define. In this case we have this n function we define here as 1 over R, H over R. And then in green we have, in this case, the radial coordinate of the event horizon, which is an input parameter of the problem. So if anything is green, it's the input parameter of the problem. Then, well, this, although it doesn't seem, the Kerr solution can be also written on that specific way as an ansatz matrix, but will be written in the non-standard coordinate system. And for that, you can relate the Boyle linguist coordinates with this new system, with this expression. So here R and big RH are the radial coordinates in the radial of the event horizon in Boyle linguist coordinates. And this A here is just the reduced angular momentum. So angular momentum over the mass. So you can then write the F functions in terms of the Kerr metric quantities. It's a bit confusing, a bit complicated, but you can do that. So here we have, again, RH, the radial coordinate of the event horizon. And also have here this CT, which must be negative. And it's a constant that doesn't have a transparent meaning. But if you look at the case in which CT is equal to 0, this will be apparently related with the non-stationarity of the solution. This can be further verified when you compute the physical quantities. So here we have the angular momentum, and if you put CT to 0, the angular momentum 0, and the horizon angular velocity is also 0. So you can have a sense what this CT is, but from outside that, it's not very, very meaningful. So now that we have a metric, we have to impose boundary conditions. Since we want a regular stationary axial-symmetric and asymptotically flat solution, this will impose some restrictions for the functions in the boundary conditions. For the asymptotic boundary conditions, it's quite easy to see that since we want asymptotically flatness, all the f functions and the w function must be 0, must go to 0. Then for the axial boundary conditions, axial symmetry and regularity implies that on the poles, the derivative of the f function and the w function in order to theta must be equal to 0. Also, since we don't want to have conical singularities, there is the f1 must be equal to 2 f2 when we are on the poles. We don't impose this as a boundary condition, but we'll use this result as a test for the numerics. Then, since we have also a symmetry related to the equatorial plane, we can compute everything just in a region from theta goes to 0 to pi over 2. If we do this, then we also have to impose that on the equatorial plane, these derivatives of the f function and the w function also must go to 0 on the equatorial plane. Then just have to then go to the event horizon boundary conditions, and to do this, it's easier to do coordinate transformation of this type. This way, when we are at the event horizon, x equals to 0. So we can do a zero expansion of the function, and we obtain this result. And here we see that the w function must be equal to omega h. This is a constant, and as you see, it's green, so it's an input parameter of the problem. And this can be understood as the angular velocity of the event horizon. Then, so with this expansion, it's quite natural to impose that the derivatives of the f functions must be equal to 0, and that the w function must be equal to the horizon angular velocity at the event horizon. Now that we have the metric and the boundary conditions, now we just need the equations of motion. These are computed through the Einstein equations, so in this case, the vacuum Einstein equations. So to do this, and to be easier for analysis afterwards, we'll keep the radial coordinate that I showed in the last slide. So here we have to rewrite the ansatz in this way, in this new way, since we impose a new radial coordinate. And if you want, you can try to prove that this h function and s function are equal to this. So I can leave you as exercise if you want. So now that we have all of this, you can go to Mathematica and use it to obtain everything that you want. So for that, here I have the first notebook, which is the equations of motion _ Kerr. So here we start by this first lines is just to clean all the variables that can also be used by other notebooks. So first we introduce the number of dimensions and the coordinates and the metric. With this, you can compute the inverse metric, the determinant, and the square root of minus the determinant. Here, these two lines are just to simplify a bit the notation. It's not very tricky or very, you don't have to do this. Then here, just some prints to see some quantities. So now we have to compute the crystal symbols. So you can do this. This line here is just to print the non-zero components of the Christoffel symbols. Also, I use the symmetries of the quantities, so to be a bit faster. Then with the Christoffel symbols, you can compute the Riemann tensor. And with that, you can go obtain the Ricci tensor and finally the Ricci scalar. So you have now the Einstein tensor, which in this case is the equations of motion. You can compute, and here we, instead of using the covariant version of form of the Einstein tensor, we use the mix. So one index is covariant, the other is contravariant. Then you can also compute the Kretschmann scalar. This is not an important step, but it's useful to see if, when you obtain the solution, if the space-time is smooth everywhere, if there is no divergence. Then here I have a part for the energy moment tensor, since we want the Kerr solution that is equal to 0, so not a very important step. Then we have basically the full equation. So here, instead of using all the equations are as they are, you will do a combination of the Einstein equations. This is done because CADSOL likes to have all the PDEs written as having only one function with second derivatives. So he wants, for example, for the first equation, he wants that to have only the second derivatives of the f1 function, for example, and the second one for the f2, and the third for the f0, and the fourth for w. So you have to do a combination of these Einstein equations. You can do this in this way. That will give you exactly what CADSOL wants. Then you also have another two equations that will be used as constraints. They will not be solved by the solver, will just be computed with the solution that you obtain, and will be basically just to see if the solver obtained a good solution, if everything went well. So here I do exactly that. So it's not very interesting, but then you can do the print just to see how the functions are. Here, as you can see, the Kretschmann scalar has a lot of terms. Then, with the equations of motion, you can now do a series expansions of them in the boundary condition, or in the boundaries. For that, we have the series expansion underscore Kerr notebook. So here, first I clean the variables again and input the equations of motion, as you can see. Sorry. Here. And now, for the expansion on the horizon, where x equals to 0, we have to redefine again, or introduce again, the h function, the s function, since they depend on x. And then we can do a power series of the functions in x, as you can see. So, doing the first ordering approximation, you obtain these results. Since each one of the equations must be equal to 0, then these results also must be equal to 0. So, for example, from this equation, you see that for this to be 0, either wx or the derivative of w must be equal to 0. And if you look to these other four equations, if one of them is equal to 0, then the other must also be equal to 0. So you conclude that wx must be equal to 0, and the derivative of w must be equal to 0. Therefore, the w must be equal to a constant. And here, you say that the constant is omega h. Then, going for the first ordering approximation, we do the same. And from these two equations, we see that f2x must be equal to 0. This implies that on the third equation, f0x must also go to 0. And finally, the fifth equation, we see that f1x also must go to 0. Then this last equation basically says that the derivatives of f0 must be equal to the derivative of f1. This implies that f0 must be equal to f1 plus a constant. This is related to the fact that on the horizon, the Hawking temperature must be constant. This is basically related to this result. So we also impose from what you see before that the f functions x must be equal to 0. This is exactly what we all see for the Monod conditions at the event horizon. So the derivatives of the f function must be equal to 0, and the h function must be equal to omega h at the event horizon. If you do the same for the poles, on the pole, you can do exactly the same, but now the power expansion is on theta instead of x. And you could do, as I said, they're exactly the same. So here we see that f0 theta must be equal to 0. Here we see that f1 theta must be equal to f2 theta. And here we see that f1, the derivative of x1 must be equal to the derivative of x2. So we write this. So this result here, f1 must be equal to f2 plus a constant, is associated to the conical singularities. In fact, this constant must be equal to 0 because of that. Then going for the first order approximation, here we see that f1 theta must be equal to 0, so f2 will always be equal to 0. And we see that delta theta must also go to 0. So we say that. And again, this is exactly the same result that we impose for the poles, that the derivatives of f1, f2, and f0, and the derivative of w must be equal to 0. So now that we motivated a bit more why we choose these boundary conditions, we can go and print everything that we obtained so far in the Fortran form, so that we can compute copy everything to Fortran file. But before we do that, the radial coordinate that we use goes from 0 to infinity, but computers don't like very much infinity quantities. So it's useful to use to impose a compactification. And one way of do this is basically doing this coordinate transformation. And since we do this coordinate transformation, the derivatives will also change, and will change in these factors. So on the Mathematica file, you can say that. So here we say that f1, f2, f0, w are equal to u1, u2, u3, and u4. And the derivative, or the first derivative, in order to x, or to the radial coordinate, will be this ff squared times the derivative, which is, if you look to this, is exactly ff is 1 over x bar. Doing the same for the second derivatives, this is exactly the same. You can do everything. And now we have here, we write the h function and the x function. So here we just say that is equal to this name. And on the Fortran file, we'll specify the expression. It's a bit long, so that's why we do this here. And then on the Fortran file, we specify the function. Here we just rename the mathematical functions for the sine, cosine, and the others to be a bit easier when we write everything on the Fortran file. And we also do the same for the exponential. Now, for some apparent reason, Fortran doesn't like very long expressions. So it doesn't like the expression to be in just one line. So we have to basically shrink the width of the page to some value, so a bit smaller, so that when you print everything, or for example, the first equation of motion in Fortran form, you get something like this. Mm-hmm. No, I know. I know there should be a reason, but I didn't know which was. But yeah, it makes sense. So you can do the print, and then you have just to copy this to a Fortran file, as I will show you next. And just to finalize this part, as I said, you need the Jacobian. So you need to do the derivatives of each equation in order to each function and their first, second derivatives. So here for the equation 1, we do the derivatives with respect to the function 1 in the derivatives. So we get some result. Then for the function 2, f2, then for the third function, and then for the fourth. And we have to repeat this for the remaining 3 equations. So as you can see, that will be a lot of small expressions. Now, with this done, okay, with this done, you can go to, let me just go there. Not here. You can go and print everything for the Fortran file. So the first one is this 2C to CAD.f, and this is basically the brain of the solver. So within this file, there are several subroutines which are appropriate for some type of problem that you have. So in our case, we want to save or want to solve an elliptic problem. So we use some specific routine. But if, for example, if you want to solve a parabolic problem, you use a different subroutine. Since this file is the brain of the operation, you should not mess with him. Leave it as it is. No, don't change anything. Then we have the file that we will change, and here is where everything that you compute so far, we'll put everything there. So you start by defining some parameters for the solver. There are a lot of them. I'll just mention some which are a bit more important. So the first one, or the first 2 ones, are the number of points in the grid in the x direction, in the y, the x and the y direction. This PD is the consistency order for the linear solver. Then this ILN1 is the solver that you want to use. So he uses numbers to define or to specify which solver he is. Sorry. Then this NK is the number of equations that you have to solve. Then, for example, this LY, LX, LY, and pole is if you want to, or if your boundary conditions are circular. So if they repeat themselves. In this case, it doesn't, so you put as false. Then there is a lot of code for the solver. This has to do, say, with memory and so on. It's not very, very important here. So next we have the parameters of the problem. You have to input what are the parameters of the problem. So the first one, as we saw, is the event horizon, and the second one is the horizon angular velocity. Here we put these values, for example. Then there's also this subroutine, which was developed by Dr. Eugene Radu, that when, in this case, since we have a Kerr solution, we can use as an initial guess the Kerr solution obtained by the equations that I show you on the presentation. But if you use Mathematica, for example, to obtain what are the values of the f functions in the double function, Fortran doesn't like very much the way that it's written. So this function, or this subroutine, what does is read those numbers, put everything as Fortran wants, and then print again everything. So when you use that file as the initial guess, Fortran will not have any problem with that. So here is when we begin the iteration for the Newton-Raphson method. Usually you use 3 iterations. Usually it's enough to obtain good accuracy. Of course, you can do more if you want, but usually 3 is enough. Then this is some part of the code. And here it's where we start, you'll go get the initial solution, which usually is on this file, on this name file. Then, again, a bit more code. Here is where the real code begins. So basically, here he calls the subroutine, which is this one in particular for our case. And here is when you do exactly the Newton-Raphson method. So after this, after the computer, it will print everything. So in this file, we'll print the untyped functions, f1, f2, f0, and w. He will also print the arrows, print the grids, so the grid associated to the x direction and the y direction. And here we'll print again the functions, but in a different way. And finally, we'll print the parameters, the input parameters of the problem in this res file. But yeah, basically this is the solver. But where do we put the equation of motion and the boundary conditions? This is put within some subroutines that are within the subroutine that we call. In this case, there are 4 subroutines. The first one, this one, is where we put the equations of motion. So here, first, here are the definitions for the function. So f1 is u1, sorry, is f1. So in the Fortran file, this is represents the first function. So it's the same for the other 4. Here you have the derivatives. The first derivative in order to x, in order to y, the second in order to x, and the second in order to, to y in order to x, and the mix. So here, first, we use the same terminology that we did on the Mathematica file. Unfortunately, we cannot use x here as we did in the Mathematica file because x is used for another thing on this Fortran file. So we call it r. So if you want to copy the equations to here, mind that you have to change the x to r. Then here we have the f function, the s function, and the h with its derivatives. So you can now print or copy and paste all the equations, the equation of motion, the first one, the second, and the others. The way that the solver knows that which are the equations that he has to solve is by doing this small lines of code. Basically, here you're saying that, or you're saying to the solver that you want to compute basically the Newton residual for equation 1, equation 2, equation 3, and equation 4. So since you want that to be as small as 0, the solver will try to solve that and try to obtain this as close as to 0. Then, in this case, the energy momentum tensor is 0, so it's not very important. And here we also put the Ricci scalar, the 2 constraint equations, and the Kretschmann scalar. As you can see, the Kretschmann scale is quite long. And at the end, for these 4 equations, you only will compute them. You'll not use them to solve anything. You just take the solution that you compute, substitute everything on these equations, and then do a print for a file. So the second subroutine is associated to the boundary conditions. And here is where you'll put all the boundary conditions. The way that you do this is by using the goto function of Fortran. Unfortunately, Fortran likes people normally like to use this goto function, but it's quite annoying to understand what is happening exactly. But here we have 4 labels, 10, 20, 13, and 40. And each label corresponds to a boundary condition, or a boundary. The 10 label corresponds to the boundary at the event horizon. The 20 corresponds to the boundary at infinity, spatial infinity. The third, or the 13, corresponds to the boundary at the poles, and 40 corresponds to the boundary at the equatorial plane. So for each label, so for example here it starts the label 10, you can put the boundary conditions. And the way that you do this is using again the Newton residuals, which here I have an example. So at the event horizon, we saw that the derivatives of the f function must be 0, and that w must be equal to omega h. If you rewrite this such a way that we have everything on the left equal to 0, then you just have to tell the solver that you want to find which are the function that solves this equation. Basically, try to find the zeros. So in the same way that you did for the equations, here you can do exactly the same for the boundary conditions. That is exactly what we have here. So here we have the derivative of x of the first function that must be equal to 0. The second one, the third one, that also must be equal to 0. And here we have that the w function minus the omega h, which here we call small w, must be equal to 0. You can do this for the other boundaries. So here for the infinity boundary, that all the functions must be 0. So it is. And you can do again for the poles and the equatorial plane. Now, here is the fourth subroutine, but it's not very important, so I will not talk about it. But then we have the third, the third subroutine, in which here is where you put the Jacobians matrices. So as you can see, that will be quite a pain to copy everything and put everything. So here we do the same for the functions, and the same for the R variable, the FEF, the X, and the H functions. And here is where you start to put all the entries of the matrices. So as you can see, there's a lot of them, and most of them are 0, so it's a bit easier, but it's quite tireful. Well, it takes a while to put every single equation here. But when you finish this, you basically have everything done. So you just have to run the code. And for that, depending on which OS you are using, for example, for Linux and Mac OS, it's the same. I didn't check for Mac OS, so if I'm wrong, sorry, I don't have a Mac OS to test that. But at least for Windows and for Linux and Windows, this is correct. At least when I try it on my PC, which has Windows, and my desktop at home that has Windows, it worked. So to do this, you just have to run these 3 lines of code. First, you run the brain of the operation, the do CAD.f file, and use 2 flags. The first one, the /c, is a flag to not link the outputs. Basically, what this means is that when you compile, you'll get an output file, which in the case of Linux and Mac is .o. In the case of Windows, it's .object. So basically, it's an object. It's not an executionable file. With this, you can then use in this line that output to run everything. This O2 flag is just an optimization flag. By default, the Fortran already does this, so you could omit this. It's not very important. Then we do the same for the v1 file, which is the file that we altered, and we put everything there. We do the same, and with those 2 outputs, the .os or .objects files, we run those 2 together, and then we link them together basically, and we output this as executionable. So then you just have to basically run that file. So I'll show you how to do this. So here I have the 2 files, the 2 Fortran files, this one and this one. I already have the outputs from the 2 initial codes, these 2. This one will give you some warnings, some remarks, but it's not very, you don't have to be worried about that, unless if you get an error, that's a different case. But it takes quite a while, so I will not run here. Then for the v1 file, it should be quite fast. Then with that, you can do iFortran with the outputs. And you will have an output, which here I call it run Kerr. If you did this, Sorry. For in the case of Windows, I forgot that. Oh, sorry. For case of the Linux, when we install this compiler, we have to source some variables within the Fortran compiler. So you have to run this code. Everything you open a terminal to be able to use the Fortran compiler. So you can now run and it run. So you just have to now run this executable. Doing this, sorry, yes.
You could just add it to bash RC, right?
Yes, it's true. Yeah, it works. But yeah, I didn't do it myself, but yeah, you can do that. In principle, it should work. So
okay, good.
Thank you. So this is the output of the CADSOL. So there's some parameters in the beginning, so there's a lot of information here, but the main points that I want you to focus on is first on this, which is the Newton residuals. As they are the Newton residuals, they should be close to zero. And as you can see, this is already very close to zero. This also happens here because we are using the exact solution as initial guess. So usually you will not have -7 or 10 to the power of -7 on the first iteration. And in principle, after the third iteration, you have quite good results. Then we can also look as, for example, now that the solver run a bit more, as you can see, the residuals are a bit better. So 10 to the -9 and 10 to the -10. And here you get to the -11 power. So the second one, so here it ended the first iteration. So you will also do the second in the third iteration. But let's look at this. The second thing that I want to look is basically this. This says that the solver computed the solution and also provided the error. So if you run it and you get this expression, this phrase, then in principle, everything is good. The third and last part that I want to show you, that I want you to look at, is the relative norm of the errors. So basically this. This is basically the errors estimation for each function. So F1, F2, F3, and W. Sorry, F1, F2, F0, and 1, and W. So since this is an error, you expect to be close to 0. So now I can show you, principle, the last iteration. So it's still finishing. So from on the third iteration, you can see that the residuals are not, well, are a bit better, but it starts to get to a point that it cannot get any better than that. And so it finished, the third iteration, and as you can see, everything went well. And the relative norm of the errors, as you can see, didn't change any much. So this is basically what the best you can get. So that's basically it. That's what I have to show you in this first lecture. If you have any question, please do so. Tomorrow lesson, I will give you some solution of a Bose star, of a rotating scalar Bose star, and we'll start to see how to obtain some physical quantities such as mass, angular momentum, and other quantities. So, thank you.
Okay, George, thank you very much. Thank you very much, John, for, I see you guys, you really have quite, this is almost a factory.
Basically,
it's numerical, so it's really nice.
Yeah.
Okay, so questions? Online questions? I don't see questions in the room. It means that it was very clear.
Or not clear. Come here.
Right at the beginning, what are the criteria for the choice of the relaxation parameter?
On the file or the?
On the slides.
On the slides, okay. So
We are introducing the method.
the method. So you were talking about the. So
Yeah.
here.
Yes, yes, parameter.
Yes,
Yes.
is a relaxation factor is basically always equal to 1. It's not very important, but what this does is basically like the learning rate in in deep learning. Basically, if you take one solution, and if you want to jump very far from the first solution, or if you want to jump close to that solution, if you see if this x function or s factor is close to 0, then this new improved solution will be very close to the original one. But if this s is like 10 or 100, this new solution will be quite far from the original one. But in most of the cases, it's just equal to 1. For example, for the Newton-Raphson method, in general, that factor is equal to 1. It's not very important.
Thank you.
You're welcome.
Okay. So, any more questions? We still have, if you have questions, we still have some time. Yeah, we still have some time, but
You can start the next one a
if
bit early.
not, we can start with the next one.
You can just have a 15 minutes break.
Or maybe that's even better. Yeah. So okay. So I think a suggestion from Carlos, which I agree, is we start at 3 and we make a 10 minutes break approximately. Okay.
Thank you.
Okay. So let's talk in 10 minutes then.
Okay.